We come to the last section of this very long chapter, and it's entitled Electrolysis 20.9. These are non-spontaneous redox reactions. They require electrical energy to cause the non-spontaneous reaction to occur. It's very important in industrial metal processing. We'll talk about that. Contrast this to a voltaic cell, which is based on a spontaneous slide on the first page, where we saw the electrolysis of the cell. Rarely does anyone ask you to draw it. What they will ask you are what action. So let's give a good example. Let's talk about molten sodium chloride. What happens is 2 graphite electrodes are inserted into melted sodium chloride. When that happens, there are 2 observations. First of all, there is the pale green chlorine gas. Secondly, there will be some sodium metal liquid that is floating on top. Now, this is the Whal process, and it was actually developed right here in Ohio by Whal when he was only 21 years old. And it led to the formation of the Alcoa Corporation, which maybe you've heard of, that primarily produces aluminum. But here we're going to talk about the chemistry. Based on what they saw chlorine gas. Well, chlorine gas, if I have sodium chloride as an ionic liquid, that meant we had to have chloride ion. That was the oxidation process. Oxidation occurs at the anode, and when you take a look at the chart, you will see that the E0 of reduction is a positive 1.359. They also observed sodium as a liquid. Well, that was in its zero oxidation state, and it came from sodium plus the ion. That, again, we've taught in 1210. When we add these 2 together, what we come up with is the net chemical reaction for the molten sodium chloride forming sodium liquid and chlorine gas. If I do my E0 cell calculation, it would be the E0 of what is being reduced, which is the Na plus to the Na, and I would subtract from that the value of the E0 of what's being oxidized, Cl minus to Cl2. Notice that the E0 cell is a negative number. Again, this is a non-spontaneous reaction. The equations that are involved. So we have our oxidation and we have our... So when we do electrolysis, we label the electrodes. And I guess since I've taught this 2 years ago, labels have disappeared. So this is how I learned it, but again, we are not going to label it. What I'm going to do is move back to the reduction. So what still holds true is as the Na plus is depleted, additional Na plus moves in close to the electrode. As the Cl minus is oxidized, additional Cl minus moves in close to the electrode so that they can come in contact with the power source and cause the reaction to occur. When they do this in industry, they have to keep the 2 material products apart or they will react to explosively form sodium chloride. So another thing they cover in this section is electrolysis if you have an active electrode. This is primarily used for metal plating. If you've ever had a cheap piece of jewelry where it looks like silver, but it also turns green after a while, it's because there was a metal plated on top of a substrate that's a lot cheaper than the metal itself. Here's how it happens. A metal electrode will be oxidized if the potential is less positive. So here we have the oxygen reaction, and that's going to undergo the reduction. And as the line says above, this will undergo the oxidation. Once the nickel is formed by oxidation, it is reduced more readily than water, and there is the E cell reaction. And what will happen is the nickel will deposit on the cathode. I'm not going to go into more detail because I don't think they ever do. I just want you to be aware that it is a way to plate certain metals on substrates that are less expensive. What you might see on an exam is what are called the quantitative aspects of electrolysis. This goes all the way back to 1832. 32, where Michael Faraday observed that the amount of a substance that undergoes oxidation is proportional to the amount of electricity. Plus 1, 1 electron. Plus 2, 2 electrons. Plus 3, 3 electrons. Those were the reduction processes. And he determined that the quantity of charge will be measured as a coulomb, and a coulomb is 96,000, I believe it is 485 coulombs per mole of electrons. That is a Faraday. What we're going to be using are both of these conversion factors in our calculations. The questions we're going to ask are, how much product can you form during an electrolysis, and how long could it possibly take? So the way we teach this is we have an example. We say palladium is being produced by the reduction of palladium to ions. We are passing 3.2 amps of current through a solution of palladium sulfate for 30 minutes. So while I said time, what this one really does is it talks about a mass. This is simply a dimension analysis problem that you learned back in chapter 1 in 1210. If we take 3.20 amps and we do a conversion that says 1 amp second is a coulomb, we then say there are 60 seconds in a minute, and we are running this example for 30 minutes. What we will come up with is 5.76 times 10 to the third coulombs. Now again, you're saying like, why? But essentially it is a method that we use to calculate the mass. We go from amps to coulombs, coulombs to seconds, get rid of the seconds to get the number of coulombs that it took to drive this reaction. So it can be done in many ways. I have always broken it down into 2 steps because it fits on a blackboard, it fits on a screen. So essentially, what we will use here is we will say 96,485 coulombs is 1 mole of electrons. The half reaction for palladium, it requires 2 moles of electrons for every mole of palladium. And this one you're going to know already. 1 mole of palladium weighs 106.2 grams of palladium. That gives us 3.176 grams of palladium. Again, we have found the mass that we need in order to, we have found the mass that we will obtain if we pass a 3.2 amp current through a solution for 30 minutes. So really, our 2 variables are the amperes and the minutes. So this is the reduction reaction. There also has to be an oxidation reaction, and that is how can you find the mass? And you may be asked this on an exam. You need to set up the dimension analysis on the next slide. If we were doing this in air, we would see oxygen being the oxidation portion of this redox reaction. We might want to know how much volume of oxygen is produced when we're doing that reduction. I'm going to use that same 5.76 times 10 to the third coulombs, and I'm going to say 1 mole of electrons is once again 96,485 coulombs. I will say 1 mole of oxygen requires 4 moles of electrons. There they sit in the equation. And going back to the gas chapter, I will assume that this is an ideal gas, 22.4 liters for every mole of oxygen. That would give me 0.334 liters of oxygen are produced. Now, I'm going to write it right here. Oxygen is harmless. What if we were producing hydrogen gas? Well, if there is a spark, that is explosive. So essentially, you got to look at it on a case-by-case basis, but what we've shown here, you may be asked what volume of oxygen would be produced. This is also a short section. So essentially, there's one more type of technique in 1220 that we can use with electrolysis, and that is to find an oxidation state. And you're going to say, like, how are you going to do this? Well, let's say an oxidation state is the moles of electrons divided by the moles of the material. In this case, we have gold. They've told us 835 coulombs. They've told us the number of grams of gold. So we're going to just do two very short calculations. We're going to take that 835 coulombs and we're going to say 1 mole of electrons is 96,485 coulombs. And it says in this problem, there are 0.08653 moles of electrons. Okay, so that's the numerator of this oxidation state expression. Then we're going to take, and maybe you figure this out, 0.568 grams of gold, and we will say 1 mole of gold weighs 196.9 grams of gold. That is going to give me 0.02885 moles of gold. So I've got my numerator and I've got my denominator. So I will now say, what is the oxidation state? I'll take my moles of electrons, 0.08653 moles of electrons, and I will divide it by my moles of gold, 0.02885 moles of gold, and I'll come up with the number 3 moles of electrons for every mole of gold. And that will tell me that this example has gold in the +3 oxidation state. Now, we've wrapped up this chapter. We've touched upon some applications, but what you really should take away from this is the redox foundation. Be able to recognize what is being oxidized and what is being reduced. Be able to find an E0 of a cell. Be able to take that into a delta G. Be able to take that delta G into an E. And as you notice from a practice midterm exam we've talked about in class, sometimes you need to take your E0 of your cell, turn it into an E of a cell if you're given concentrations, and from that come up with a K. A challenge, but it's an awful lot of powerful information.